coming up next here is a speaker that I'm really happy to have here for a college about knowledge first AI. This may be the person to really go to on what knowledge first AI really is. Professor Jude Shavlik from the University of Wisconsin in Madison has actually been working on knowledge first AI for the better part of the past 30 years. Back in 1994, he published a paper called Knowledge-Based Artificial Neural Networks. And ever since, he hasn't really slowed down. He's been at the forefront of incorporating knowledge with machine learning that entire time, working on projects with DARPA for interactive learning between machine learners and human teachers. And he's also been working on projects with groups like the National Library of Medicine for integrating physician expertise with machine learning for breast cancer diagnosis. But all around, I'm really happy to have Jude Shavlik up here because, I mean, when it comes to knowledge first AI, I feel like he's the guy to go to, and he's here to share some of his expertise with us.
All right, hopefully you just see one slide in not presenter mode. And thanks for introduction. Here's how I changed over 40 years, actually probably only the middle 30 of it, but not too bad, I guess. Okay, so I thought I'd organize this talk. It's not a real long one, and it's 40 years, so it's only like, how many seconds per year? I don't know, not too many, 30 or something, 20. But I'd organize it around some maybe key points that summarize 5-6 years of working. Okay, so when I was a grad student, we worked on something that was about knowledge-intensive machine learning. We were trying to react, and it was a real exciting time as a reaction to more just counting and statistics and the old stuff. Whenever you're a grad student, anything more than 3 years is ancient. And so there's an exciting time, something called explanation-based learning. It didn't pan out too much. At least I'll explain a little bit why, and you probably haven't heard of it. But I think it's at least good to know some history. And the idea, this is a picture. It's an interesting story behind it. You'll have to ask me later, though. This person here, if you can see my mouse, but the standing up guy to the left, he's kind of the machine learning algorithm we're trying to capture. And he's noticing the person over to the right doing something intelligent. This is about reasoning, like in the last talk, and about knowledge and such. And this person is not burning his hand because he's using a stick. I added the red part. That's not in the original Larson cartoon there. So that's what we were trying to do. We were trying to explain, like, he met an important goal. He didn't burn his hand, and the stick kept his hand distant from the heat, and didn't get bogged down in that his clothes was over the left shoulder instead of the right. He wore glasses or not. He was on a rock and not standing. All these things that if you just learn from pure labeled examples, you need a lot of examples to focus on that stick being important. Okay, but the problem here is we needed a lot of knowledge to do all that reasoning, and it was fragile. It's just hard to capture all that, and I think it still is hard these days. There's improvements, and I'll talk a little bit about some logic stuff too, like the previous speaker at the end of my talk. But it's pretty hard. And what if it's buggy? And how do you want to build on a house of cards? Okay, so that led to what I started doing after I finished my PhD, and did it for about a dozen years or so. Some pictures of some students. Jeff Towell, I can't find a picture of him. He was my first grad student there. He's just GT on the bottom. And what we and others worked on trying to take some initial knowledge and use machine learning to improve it. The approach that my group took is drawn here. We started in the upper left with the some knowledge written as rules, some formal notation. But what we did is we compiled it. We inserted it into a neural network. And I'll give you a little flavor of that in the next slide. And we had some training examples, some input-output pairs, and we did backprop with some minor little differences, but basically backprop. And we had a trained network. And another thing we worked on, and it's increasingly important, I think, these days, is reversing or decompilation, if you've ever heard that term. But here we called it rule extraction in those days, explaining what that neural network learned. And you get a new rule base, and you could even go around in more loops, edit it as a human, and train it with a machine. And this curving line is supposed to show like the symbolic, the division between symbolic and numeric or neural or connectionist or what learning. Now there are other people that work directly on the symbolic manipulation, and there's a little bit in the previous talk as well. I'm not doing a whole survey here, but there are some out there. Okay, so how do we do that? Well, I remember hearing a talk from Jeff Hinton in the Machine Learning Conference in 1988, and he said, you can backprop through anything. And I was starting to think, well, how can you backprop through a rule base? And what it turned out, in hindsight, maybe not that surprising, that if you look at a rule base, especially just propositional logic, there's no variables like in the fancier parts of Prolog. But if you look at it, there's some things that are just supporting facts. You don't unwind any further. There's some things you want to conclude. You don't want to go beyond that. And there's a bunch of intermediate conclusions. Now, if you look at that, we've been seeing neural networks for a long time. And of course, that looks just like a neural network. It's a graph, right? And that's what we did. We took the rule topology, the graph structure that a rule set induced. We could also have recursion with some recurrent neural net links. I didn't show those here. And we added some extra links that had more or less epsilon weights, random to minus to plus epsilon randomly, and some extra nodes. I just drew one on the right here. But we fully connected like a standard neural network. The dotted lines is like a standard neural network, but in a sense, we union two neural networks, one that looked just like the rule base and another standard neural network. And some of the parts of the rules, like maybe this part of the rule didn't matter and it goes to zero, but maybe this feature input was important and it got replaced, and you could add some new intermediate rules and some more other layers and stuff. So that's his first insight, that a knowledge base, a KB for short, provides a graph that can be used to initialize a neural network. We were actually kind of worried about deep networks. I looked way back in our early papers. We talk about deep networks, and we were worried about the gradient getting too diffuse. And we were scared. Everyone said deep networks were a bad idea, and that scared us. And but in a way, we were kind of making deep. We didn't make that big a rule bases. They weren't 100 layers deep or anything, but they were kind of in that flavor a little bit. So how do they work? I'm just going to have a cartoon drawing of it all here, but we have papers. There's actual results from real data sets from a variety of domains, and they look a bit like this. So what are our axes? Well, the non-training data we'd use, what's sometimes called a learning curve, and then the error on held aside test set data and cross-validation and all that kind of stuff was used in parameter tuning. Okay, so a standard machine learning thing here, artificial neural network, this green line, it kind of goes down as you get more data and plateaus. That's kind of standard. And if you just wrote a rule base, you probably have some intelligence and you get this horizontal line, though, because you don't maybe debug it on the first few examples, but you only debug on like, maybe like on 10, sorry. Oh, geez. Computers are too trigger happy. So sorry about that. And so back to this, the blue line was we put our knowledge in. It's not perfect. It has some kind of errors, and it doesn't improve because it doesn't do, or at least doesn't improve by a machine because it doesn't do learning. And our idea was to take both these ideas, start ideally right here. Sometimes because of our algorithmic constraints, we had to approximate that. So I put this a little higher to illustrate that point. And we would get a better curve because we had a better starting point. So one way I like to think about this use of prior knowledge is if you have an algorithm that has kind of an incremental behavior rather than a batch like a decision tree algorithm, if you know about that, but a neural network, you get a small batch, not a batch of all the data, a small batch of examples, and you adjust the weights a little bit, right? Then you get another chunk of examples, and you do that over and over. Well, why don't you start at a smart place instead of a random place? The green line starts random, the red one started an approximation to the blue knowledge there. Okay, so if you have so much data, you care about a learning curve, you care about the end of your learning curve really more so, and then you're going to get a lower error rate. If we got a lot of data, these lines come close, and the first talk talked about small data, and that I think is kind of illustrated here. So if you had a spec like to go to market with your product, you had to get lower than, I don't know, let's say 1% error rate or something. Then then you have this is your spec, right? This white horizontal line here. This approach takes this long to read it, maybe reach it, and maybe that's 100,000 examples. Uh, but with some domain knowledge, you might get by with just a small amount, just like the first talk today. That was a great talk. It really matched a lot of my motivations for 40 years. So I'm glad it happens. I knew sooner or later it would. I hope this is the time where knowledge intensive learning wins. Okay, now I forgot what to say. The second insight was, that you could initialize a neural network. So the third insight I think we had along the way with the student up there, Rich Macklin, is that it's not really prior knowledge or domain knowledge or initial knowledge. It's really knowledge that should come at any time in some kind of continual learner, especially happens in what's called reinforcement learning. So that's kind of the idea here. Here again, we have some training here because it's like playing a video game, and so it's an arbitrary scale in a way, but higher is better. So if you do standard reinforcement learning, you get a green line like that. But if you notice right here, like the player in the game that you as the human are trying to teach, it's doing something stupid. You can tell it's something, and it does a lot better. Run towards and run away from bad things, which kind of sounds silly. I think, what is this green line learning? Because if we tell it the most obvious thing, it would get a jump in performance. You could also give another hunk and it would go a little higher. There's a little bit of law of diminishing returns, but ideally you get continual knowledge. So as we say in the modern era, and if you see something, say something. You say that. Like I live in New York now, and the subways are signs like that. Okay, so you really should think of prior knowledge as something that continually comes in, and learning is something that continually happens. Okay, now someone asked, I think, the first talk about what if that knowledge is bad, and that's what I said was a problem with explanation-based learning, is we could be building on a house of cards, and it's going to collapse sooner than we'd like. So we did experiments, like we said, run towards the bad things and run away from the good things, and other more interesting things than that. And not surprisingly, you get a big degradation in performance. This one was I don't know, it was green maybe on the last slide, but this is just standard reinforcement. If you give advice here, but you get bad, but because it's a learning system, it can recover. And sometimes bad advice, even asymptotically, led to better, because in reinforcement learning, it's an active agent, and it learns what to avoid and things like that. Okay, so, but there's a problem, that leads to our fourth advice, that it's hard to write domain knowledge, and expert systems were a challenge, and people talked about psych, and I'm a big believer in knowledge bases and rule bases, but it's hard. Now, where does most of knowledge, up until the machine learning revolution, where's most of the knowledge come from? Well, it's in a sense, we put it into computers by writing programs or algorithms at a more abstract level. And we did some theory or knowledge refinement, the stuff I've just been talking about. Two problems we worked on. One is in proteins, and there's a famous algorithm for part of protein structure prediction called the Chow-Fast model. We could actually make a neural network implement that algorithm, and we refined it, and we improved on that algorithm. There's also something in control theory called proportional integral and derivative, PID controllers. They're linear, and by using hidden units with nonlinear hidden units, we, in a sense, made a nonlinear controller out of an initial linear controller. Now, I always liked this idea of that, and I even used this earlier, about compiling knowledge into a neural network, just like we usually compile programs in a high-level language into a machine code or assembly code or in some intermediate language for runability or efficiency. Well, we should also be thinking about compiling to a differentiation for learnability. And there's a new book on it, sometimes called differential programming and such. A recent book came out, maybe a little hard to see there, but called neurosymbolic programming. And so I think that's an interesting way of just kind of a new way to write programs in as well. Now, another thing we had, a kind of whirlwind tour here, we tried some of these ideas, support vector machines with some workers up there. And here's a standard divide and support vector machine. If you don't know, you can kind of see there's a good separating line between the squares and the circles. And but those are all points. Now, this is the next insight, that we don't have to train algorithms by labeling points, specific examples with every feature specified. We can give a rule. A rule just labels a region of the possible inputs of what's called feature space. Like men between 40 and 50 and between 200 and 300 pounds or something, right? And that's a subregion, and these are specific people, including, no, I'm over 50 now, so I'm outside that. But so that's what we did in some other work called knowledge-based support vector machines. And then we get a different separating line that you could give it data as points, you could give data as regions, and you could put weights on them and other things. It was all underlined. It all was linear programming. Okay, next. Well, where's that knowledge come from? Well, I talked earlier about rule extraction. I'm not going to really talk about rule extraction in this talk, but if you extract rules from something trained the traditional way, non-knowledge intensive, now you have some domain knowledge, especially if you're doing transfer learning. Not most of, but a lot of machine learning these days involves what's called transfer learning. Like if you know about BERT, you pre-tune it, or Google pre-tunes it, then people fine-tune it. Fine-tune it after pre-training. And so you have some task now, and you just learned that somehow or another, no domain knowledge, and you pulled out some rules by rule extraction. Well, you could give that, if you have a related task B, you could give that to the machine in this knowledge refinement stuff that I quickly went over in the previous slides. Okay, and since rule extraction is not perfect and transfer from task A to B is not quite perfect, you need some data to refine those things. Now, this relates a bit to the second talk this morning about using logics. Here's some collaborators I have over the right. Sort of the last roughly decade before I retired from the University of Wisconsin, and we worked on probabilistic logics. And I won't go too much into them. My inside point here is that propositional, what I did earlier was just propositional. There were no for all variables like these X's and Y's and Z's down here. And also you need to have rules can't be black or white. They have to have some uncertainty. So there are Markov logic networks is the one that I particularly like, but there's lots of different ideas out there. And you might have some rule that if you know X, someone is the parent of, I'll use concrete thing. John is the parent of Mary, and Sue is the parent of Mary. Well, it's not certain, but it's probably likely that the two parents are married. I don't know what fraction there. Maybe they never were married, maybe they're married, divorced, etc. Like that. But there's a lot of good inferences like that, and so we did some work in the same spirit with that. Okay, kind of the quick wrap up here. That ideally, and I don't even know there's really an insight. I just added that my last point here. That but the advice should be in a natural language. And I was excited to see that in the first talk this morning as well. So I tried working on that about 10 years ago now. It was probably ahead of the time. I think now it is really the time. I know that's a bit of a joke there. Things are different now, but maybe it is. There's these famous things called GPT-3. If you don't know about it, really look it up at openai.org or com or something. Okay, but we'd like to do that. Now, what these GPT-3 things do, this is the stuff I worked on. This is a speculation part here, not future-ish, the next 10 years. So but these big, large, what are called large language models, they've sort of read everything in the web, or lots of stuff in the web. And they do some kind of silly. They just read it and they say, what's the next word? Or if I erase a few words, what should be in that blank or masked word? And from that, they can learn. It's kind of amazing, really. It's a kind of stunning. And there's maybe even more amazing. One secondary way they learn is just changing their internal state, not from changing their weights, but changing, in a sense, their activations. That's called prompting. And no time for examples on it. I haven't worked on it, but I've read about it. I find it pretty exciting. Now, generally, people prompt standard things like going from French to English, cheese is fromage and bread is pain or something. That's my limit of French, but maybe one or two more. And then you could ask it, what to sum. And somehow by giving those few examples, just two or three, it'll know like mother is mar or something. And I think, though, it'd be interesting to start thinking about this at a higher level, not prompt with concrete things, but prompt with more general. And I think that's happening. People are prompting like, "Give me a recipe for cooking," or such things like that. So look into that. If you don't know about that, um, look into it. Oren Etzioni, the former head of the Allen Institute of AI, argues that 80%, just in the last few months I saw this, 80% of people in AI are doing stuff with these large language models. So if you're in that 20%, are you ahead or behind of the game? Well, you be the judge. Okay, so quick wrap up. And so the things we looked at, we took knowledge, wasn't perfectly correct, so we would use some data to refine it, to extend it, neural networks, support vector machines, probabilistic logic learning, particularly Markov logic networks, and we had some various applications here. And we had different views of how that might be done, making this incremental learning view, make an initial guess, then refine the weights. Or think about labeling big chunks of feature space, not just points. And somewhat similar to the first one, but technically a little bit different. Start out with some logic rule set and then add correction terms in a sense to it and continue there. Okay, and then I didn't talk much about it, but I do think reverse engineering after you refine your knowledge is an important thing. We don't want to just put it in. We want to get it back out. Maybe humans edit. Maybe it's used elsewhere in a transfer learning setting or something. Okay, so that's it. I'll try to understand the whole system. There's real good people helping me out the last couple of days getting practiced on it.
Well, thanks so much for that
Okay.
presentation, Jude. It was great to hear from you. And I thought I have my own questions of my own, but does anyone here have anything they want to ask? We have time for about one question, maybe.
Yes, thank you. So earlier, previously you did mention about the bad advice and how about overcoming the bad advice. But if we keep accumulated the bad advice, then how can the machine learning to overcome the accumulated bad advice, or if we keep having increased the iteration, then it will give the good result until the end?
Well, if you give some bad advice, I'd hope there'd be some way to get some feedback that it is, to realize it's bad inside your algorithm. In reinforcement learning, you learn that you find that because you get these rewards. Your robot falls off the cliff or something, and it gets a big negative reward or runs into the wall. And then you refine the advice by backprop or whatever learning algorithm you do. And now you have improved advice. Maybe it's less bad, maybe it's not bad at all. So you don't really keep around the bad advice. Once you know it's bad, you try to fix it. Just like it's just automatic debugging of a type, really, is the way to think of it. Yeah, sorry for that. Was as fast as I could go for 40 years, but I forgot what time
it's
I
all
started.
Right. It's not your fault. This is one of my first times moderating an event like this, and honestly, all the delays from the morning got my heartbeat a little up.
Yeah. Well, that always happens. That's just reality. Don't worry about it. People can send me email, or I'll look for chat and try to reply there too if I see there.
Thank you so much for your talk.
Well, thanks for the invitation. It looks like a great conference. Sorry I wasn't able to come out there in person. I'll be paying attention though. I'll be around for most of the rest of it. Okay. Bye now.